Okay, so we'll start. This will be unit third. Okay, so this will be unit third, and this unit is mainly about the synthesis method. Synthesis are what we call it fabrication methods. How we fabricate the nanomaterials or nanostructures. And in addition to this, there's a special section, particular section that is about carbon nanotubes. And these carbon nanotubes are very important, and it was the graphene or the fullerene or graphene which got the Nobel Prize for its discovery. So that is an important thing. In addition to this, and there is the application of these carbon nanotubes application, like in MEMS and application that is also there in this third unit. To start with, we have the synthesis of nano materials. And challenge. What are the challenges in this? Challenge means that what factors we need to take, we have to keep in mind while we synthesize or while we prepare a nanomaterial. So there are various methods of synthesizing or fabricating nanostructures, and in that case, what we have to do, we have to use a particular method depending upon our requirement, what requirement we have. Okay. Can you hear me?
Yes, sir.
Okay, good. So the goal for any goal for nanoscience, whatever you want to do with the nanotechnology or nanomaterials or nanoscience, it depends upon reliable ways to fabricate them. For example, I will give you an simple way of understanding. If you want a performance of any material, any device which is made up of nanomaterial, nanostructure, it comes from the properties of a material. Okay, what property a material has, accordingly it will perform. For example, if you have a magnetic nanoparticle, if you have a magnetic nanostructure, if it is ferromagnetic, if its magnetic moment is very large, so its performance will be better as compared to that nanomaterial whose magnetic moment is very small. Okay, and these properties in turn depends upon the atomic structure, composition, microstructure. It all depends on that. Defects and interfaces. Okay, so the properties. It's for any, not only for nanomaterials, for bulk as well. If you want to grow a, if you want to make a diode, or if you want to make a transistor, or you want to grow, make any device. So you have to control the properties at the atomic level. So we have to control the properties atomic level. Then these all things depend upon the thermodynamics and kinetics of synthesis, of the synthesis methods. So synthesis methods play an important role for any performance or it is applicability of any material, whether it is a nano or it's a bulk. So in nano materials, it is more important because you have to take care of the dimensions as well. And working at very low dimensions is very critical, and it's not easy as compared to bulk materials. So you are working nanometer range, which is not even visible without naked eyes. So you need a large microscope with large focusing power, with resolution, with very high resolution. No, there's a broad range. What is the range of applicability? There's a broad range. We cannot define it in one sentence or in one unit or in one lecture or one topic. There's a broad range of applicability. What is the range of applications? So there is a nano photonics, nano nanomechanics, yeah, nano sensors as well. You can think of very large number of applications, which we already discussed in the beginning. And the material geometries are important. What type of geometry you want to grow during the fabrication method, that you have to already also take care of. Material geometry. Okay. And this material geometry means that, like, whether you want to grow a nano rod, you want to grow a nano hole, you can grow a nano hole as well. You want to grow nano disk, you want to go nano pyramid. Okay, you want to grow a nano, this well, quantum well, which you call as, or a nano dot, quantum dot. So what material you spherical? That means if you want to grow spherical, you want to grow triangular shape, you want to grow the square shaped nanostructure. So this you have to control. Okay, that is another thing which we want to see. Now, what properties, like properties, what type of properties we need to control? Every physical property, like in the case of metals, semiconductors, and insulators, like you can have a metallic to insulating metals, insulators, semiconducting as well. You can have a hard to soft nanomaterial. You can prepare as well those. You can make an inert as well as a reactive. So all the properties can be made. If you want to luminescent, or that upper is this one, another end is quenched, where there's no transition or ready to transition, whether it is a crystalline or it is an amorphous or glassy. So what material you want to grow, accordingly the synthesis method is chosen and what properties you want to grow. Okay, so keeping all this in mind, so there is a lot of challenge actually while growing a nanoparticle. So there is a challenge, it is a challenging task to grow a nanostructure of a desired application and desired property. What property you need, the different challenges which are obvious from above, which we can see as above, different challenges or issues which one needs to take care of during growth or during synthesis, nanofabrication technique. They include that, like, can we control size? Because size is an important factor. Changing a size by a single nanometer can change a physical property. It can change the value of a particular parameter, physical parameter. Number second, so can we control the shape of nanoparticle? The another thing is that shape is important. 3. So can we control the structure of a grown particle, synthesized particle, whether it is a crystalline or amorphous? Amorphous. Number 4, the particle size distribution. Particle size distribution. What means that? That means whether all the particles will be of same size or they are of different size. What you need actually, you mostly generally people are generally when we grow some material in a during the growth process, we need the structures of the same size. So that's called non-dispersive. So these are the different challenges which are taken care by different methods. Okay, for example, there is a sol gel method, that is a chemical method. There is a lithography, that is a physical method, and there are other methods as well, and different methods have different applicability and different scope. The most general classification for the growth methods of nanomaterials or nanostructures, there are mainly two ways where from we can grow the nanostructures or nanomaterials. So there is the general classification for the growth of the nanomaterials. One is that is called as top-down approach for synthesis of nanomaterial. Number second is bottom-up approach for synthesis of nanomaterials. These are the mainly two methods, and under these two methods, there are further different methods that you see in your syllabus. They are different methods which comes under top-down approach and different methods which comes out bottom-up approach. So these are the two main approaches actually, top-down fabrication or bottom-up fabrication. So if you go to top down, that means we can't start from the top and go to the bottom. Okay, top bottom approach. It is also called top bottom approach. So you have a big block of material. You remove the part, this, remove here, remove this, remove, and you generally end up with the final material as which is a desired material which we want in the size of nanometers. Okay, so you remove all the other. In what way you remove that? Those include the different methods how you remove that part, or it means that generally there is breaking down, or there is removal or diffusion. So it generally includes removal or diffusion of bulk material. Removal or diffusion of bulk material. Okay, that means we remove it or we divide it into smaller particles, and generally we then get the nanomaterial. Okay, so method where we begin with the macroscopic dimensional material. We take a macroscopic, large size material, and like we have thin film, we have a solid powder of micron size distribution. We can have all of these types of structures which can be used for growing a nanomaterial of a particular bulk materials of which we want to create a nano, and then use a particular type of method like top-down method, and we divide that particular large size particle or large size structure, macroscopic structure, and then we reach and get the desired nanomaterial. This method top down, so it means it is either breaking down of or removal of bulk material. Breakdown removal means that this breakdown means division or divide of bulk material. Or we can also what is called a miniaturization. That means small, making it further small, further small, further small by any way, and you reach to the nanometer range to produce the desired structure with the appropriate properties, what properties we need. This is what is called as top-down approach. Okay, and its advantages are that it is simpler, and when it is simpler, then it is also simpler. It is it, but it is cost effective. Sorry, not cost effective. It is costly. The instruments which are used for particular synthesis of nanomaterials, those devices, they are costly. That another thing is that the drawback with it is that when you grow a material, a nanomaterial, with the help of a top-down approach, uh, then you can have the defects can be imperfections can be there. Imperfections can be there on the surface structure. Okay, there can be surface imperfections in the surface structure. For example, if I give you an example of this, is nanowire, which are made from the top-down approach, which are made from the top-down approach. They are not smooth, and many nanowires they contain a lot of defects. They contain a lot of defects or imperfections, impurities, and structural defects. Structural defects on its surface. Different methods, the methods which come under the category of top-down approach, they include, like, the main method is the lithography. Lithography means that printing. Litho means stone. So you make a structure on the stones. You incal the stone. So you remove a part of the stone, and there gets a pattern is, and same pattern. It is literal meaning that you incal any structure onto the stone. That is a literal meaning of lithography. Litho and graphic. So litho means stone, and graphing means that printing a pattern, creating a pattern on that. So this concept is used for nanofabrication, like in modern industries, nanomaterial, nanofabrication industries, they use the different ways of printing or creating the nanostructures with the help of this technique, lithographic technique. For example, you have electron beam lithography. You have ion beam lithography, sometimes called as focused ion beam, because you need a focused ion beam. Focused ion beam. You also have the photolithography. These two are actually mostly used, these two, because they are easy and they are less costly as compared to this ion beam. Not ion beam, electron and photo are, they are mostly used because they are not so costly as compared to the ion beam. So ion beam gives a very good result as compared to those two, but it is costly as compared to the electron beam and photolithography. Okay, and there is another method in this, what is called as ball milling. Ball milling method. Ball milling means that it is a mechanical method, and mechanical means that they momentum of balls, some metallic balls, those are striking with each other. And when they strike with each other, during the striking, they break down the material into smaller particles. So you have a jar, there is a microscopic powder and microscopic grains of the from which we want to create nano. You put up some metallic balls here, and when you put up these metallic balls here, and there's a definite ratio proportion between the weight which you want to grind, actually you want to mill, actually in this particular technique you want to use what is the weight of this pot, your weight, and the ratio of weight of these balls, weight weight of these balls. Okay, so there's a definite ratio. In what ratio will you have? There's a 10:1, so 10 grams of ball, 1 gram of the material. It can be that. So it can be 5:1. So depending upon the properties of material, so it is all seen from the literature. So what ratio we are taking. So there, this jar, it continuously rotates planetary motion, like a planetary motion at a 100 runs per minute, 1000 runs is 200 runs per minute RPM. And during that continuous motion, the balls collide with each other and they break down those powder into nanomaterial, nanostructures. Okay. And this is one, we will discuss it at later on after finishing the topics, like lithographic topics. Number, so this is another method of making the nanostructure from top-down approach. The another one is that is called as bottom up. Bottom up approach. Bottom up, as you can see the name suggests that in the bottom up approach, you have like what we call as self assembly. This is one method. Self assembly is one of the methods of the bottom up approach. You start the basic combining individual atoms, like you have individual atom, bring another two, bring another, bring another. So you form the clusters of nano clusters. Bottom up. So you start from the bottom, if a single particle, then combine them, let them combine. If they are in self-assembly, because of their kinetics and thermodynamics, they will combine up each other with each other and form the nanoclusters, nanomaterials, nanostructures. Okay, and the assembled nanostructures, they form small from smaller units. This is simply called as bottom-up approach. And the different methods which come into the category of this bottom-up approach, they include colloidal synthesis. There is another method what is called as sol gel, most effectively used sol gel synthesis, sol gel methods. These are the chemical methods actually. There's another one, hydrothermal. There's hydrothermal and solvothermal. Okay, so these are some of the methods which come under the category of bottom-up approach. And it has an advantage over top-down. Advantage over top-down. Like it has potential of creating less waste. Number one, it is more economical. It has less imperfections, and these are the advantages of this bottom-up approach. Okay. So these are two main methods, and top-down and bottom-up, two different general classification. More this what it is called it. Two main approaches of synthesizing the nanomaterials, and under these two categories there are different methods there. So those some of the methods are in your syllabus, which we will discuss one by one. Okay, I will not go into detail of any of the techniques today, but I will give you a brief idea about. See here, I think this is here. So if you see it, chemical synthesis, self-assembly, position assembly. So these are some of the methods of this bottom up and top down. Then there is what it gives chemical synthesis. It gives us particles, molecules, and it is used in cosmetics, fuel additives. Okay, bottom up is self is another way of bottom up approach. It uses crystals, films, nanotubes. So these are grown by this self assembly, and these methods are generally used for preparing the nanomaterials which are used in display applications, thin films. Position assembly. So you allow a particular atom or an ion or a molecule to locate at a particular position. Okay, it is experimental atomic or molecular devices. Okay, where we use. If you see top down, so there is a lithography. It is used for electronic devices, chip masks. Okay, quantum well lasers are made from the lithography. Computer chips are made from lithography. MEMS are made from lithography, and there's a cutting, etching, grinding. These are another other ways of using the top-down approach. Okay, and precision engineered surfaces are created from this, which are using optical mirrors. High quality optical mirrors are used. So I don't think it is not here, not this one. Sorry. Now see this. This is the lithography. I will give a brief idea about. I will not discuss it in detail. And you start from a wafer, and bulk wafer here, on which you want to grow it actually. Okay, that means you want to grow some other material on this substrate, and you can use a photolithography. Okay, then in photolithography you have an oxidation method is involved. There's etching involved. There is another method which is directly diffusion of ion diffusion. It is also called as ion implantation. That means some ions come and they diffuse into the material. They diffuse with their because of their high momentum and high kinetic energies. Okay, then metallization is another process where it's directly converted to a metal. And after all these final results, there's a packaging actually, how the chip fabrication process goes on with the help of lithography. This ion beam lithography, actually, this is that technique. And before that ion beam lithography, I will just give you a brief hint about what lithography is actually, how it goes. Lithography means that you have, for example, if you have to write something on a paper, what you need an ink, you need that particular paper on which you want to write. Okay, then apply some force. With that force you will write. The same concept is used for designing the nanostructures. Nanostructure can be a multiple quantum well. For example, if this is a substrate, you are about to design or you are about to grow a this well of some nan material, and this another quantum well of some another material. Okay, here, here. Now, it is not possible in an ordinary conventional method to grow these structures which are of dimension nanometer range, and the spacing between them here, that is of a nanometer range. It's not necessary, they may be of micron size apart, but the structure of a material is of nanometer range. So what you will do, you will take a large block of this same material like this. So it is a large thin film, for example silicon wafer, and you take this chip, you take this wafer, this is called a wafer, and you take a pattern which you want to grow. Okay, so that pattern is placed on this. Yeah, for example, you want to grow this rectangular pattern is on this. What you do is that if you want to keep that particular part here, this part, you want to keep it there, you want it there, you want to keep it there, you want to keep it there. Similarly, you have, this is the simplest case. There can be different patterns. You don't know what exact pattern it is. There may be different patterns depending upon the what we require, what application we need, what application we have. So we take some means, we have any means to remove this part which is there in between those two our desired structures. So that part needs to be removed. Now you can remove it by different ways. Take a high beam of electrons, high energetic beam of electrons, and apply on that. Okay, apply on this region, and take another beam, that same beam that is rotated and that is focused on these areas which you don't require. Okay, and before that you need to mask the pattern, because you have to mask the pattern. Okay? The masking is important, otherwise your pattern will be damaged. And once you mask it, take an electron beam, apply with high momentum and high energy. It is focused ion beam, it is electron beam, and then remove this pattern, remove these. Okay, but there are different sources for remove. There are electrons you can remove with the help of electrons, you can remove with the help of photons, you can remove with the help of ions. So accordingly we have electron beam lithography, photolithography, and ion beam lithography. Okay, and then there are multiple steps for getting the final desired result, desired product, or desired this pattern. Okay, and this is how actually simply the lithography in simple words work. So you have a pattern, and that pattern is masked, and remaining part is removed with the help of electrons, ions, or photons. There's another way of removing, that's called etching. So what etching is actually, you remove with the help of some chemicals. Take a chemical, that chemical dissolves with this part here, this part, and it removes with the help of chemical reaction. So with the help of chemical reaction, that part is taken away by that particular material, which that method is called etching. So that can be also possible. That is also used in the final process of designing a nanostructure with the help of this lithography. So you can see there's also X-ray lithography, which comes under photolithography because X-rays are photons. So if you see this, there's an optical, and in optical lithography, you have contact printing, proximity printing, projection printing. We will not go into details because this is not in our syllabus. And if time permits, then we can see. So these are the different techniques. One is electron beam, X-ray, ion beam. Then these are the different methods. Oxidation is another method. And these are the different topics which are not for we people. And if you take electron beam, so in simple electron beam, you take 10 to 50 kilo electron volt electron beam. So that is a very large energy, 10 to 50 kilo electron volt. So it is very large. Yeah, 10 to 15 kilo electron volt. And that there is no necessity of mask in this particular technique. It can be used for preparation of masks as well. And what we can create less than 1 micron to 20 nanometer structure with the help of electron beam lithography. And there is actually no diffraction limit to electron scattering actually, because electron diffraction means that electrons can diffract at the edges because they have very small wavelength, so they can diffract. That is a disadvantage of this electron beam lithography, and it is not usable for higher length features, because up to this feature there's diffraction, the low size diffraction, low size nanostructure, there's no diffraction. But whenever you go for higher structures, there can be the electron diffraction, which can create a lot of imperfections in the material. And this was created in 1960s, same technology, scanning electron microscope. It was created at that time. So it is used for actually mask making for optical lithography. We get direct writing of ICs, integrated circuits, that then optoelectron devices are created because of the electron beam method, like quantum structures, and research applications as well. Enhancement of contact, carbon nanotube probes. Carbon nanotube probes are made with the help of this electron beams. And what we need for the electron beam lithography, you need an electron gun, which is a source of electrons, and it supplies electrons. Electron column. Column means that you need some particular electron lenses. There are lenses which are called electromagnetic lenses, like we have an optical lens. So we have an electron lens as well. This lens focuses the electron beam. So you can have an electrodes on the two sides of the electron beam, which can focus these electrons into a very narrow beam. A mechanical stage, you need a stage that can move that electron beam and from one point to another. Okay, and that is a mechanical stage. It wafer under the electron beam. You can move either the electron beam. It is not possible because your electron gun is fixed. So what is done actually, then this wafer under the electron beam that can be moved. A wafer handling system that automatically feeds wafers to the system and unloads them after processing, because you once you load the wafer from which you create the pattern, you have to take it out. So that is a mechanical system that is done, that's used. And obviously a computer system which is there, which is needed. So this is actually a not a clear picture, and electron gun, you knew that it can make